All right, this is the springs section of the simple harmonic motion notes for physics. A spring system is like the object to the left here. It's a common spring system. So it has a mass of some sort attached to the spring. And then if this spring is stretched and released, it will cause the entire system to oscillate or bounce back and forth. So it would then, if I pull it this way, then it would eventually come back to here and then go this way, and then it would come back to here, so it would oscillate accordingly. When it's here at equilibrium, remember that there are no forces and it's no motion. But when we pull it, okay, we pull it so that it, or we push it in, then it has a displacement from that equilibrium. And so, or if we pull it out, it has a displacement from that equilibrium. So the spring itself supplies the restoring force on the mass, and as the mass gets further away from the equilibrium position, the force upon it actually gets greater. If you think about a slinky, the further you pull it, the more it wants to come back together. There is no force on the mass at the actual equilibrium position, like I said right here. Wherever the spring would just be at rest, there are no forces on it. So an equation that we use for a spring is Hooke's law, and it's F equals Kx, and the force is the F, and a force has a Newton, and it's the force that's supplied by a spring. The K is known as the spring constant. It can also be known as the force constant, and it actually depends on how the spring is made and what it's made out of. For example, the shocks on your car are a spring, and they're made out of really thick metal that's coiled really tight. But a slinky is made out of really thin metal, and it's not coiled real tightly, so their spring constants are different, or their force constants. And then X is the displacement of the spring from its equilibrium position, and it's in meters. Now the force constant is in newtons over meters. Don't get that confused with a Newton meter, which is multiplied, and that's a joule. Okay? So if I have an example and I have a slinky with a spring constant of 100 newtons per meter, and remember that's also my force constant, and if I stretch the slinky 5 meters from its equilibrium position, I want to know what force it's going to be pulling on my hand, the spring will be, to make it come back together. And so F equals Kx, and then F would be 100 newtons per meter multiplied by 5 meters, which would give me an answer of 500 newtons. If I did this problem on my paper on a test, I would not get full credit because I'm not showing any variables before my work. Okay, so, but pretty simple concept. Multiply, the meters cancels out, and so then you end up in newtons. I do have a video that shows from YouTube. It shows a spring system, but if you want to watch it, feel free to copy that link and then go look at it. Now, if we stretch a spring with a mass and release it, it will oscillate. This is simple harmonic motion. What is the period of this motion? Okay, period for a spring is calculated very similar to the period of a pendulum. The difference is that it's T equals 2 pi square root of M over K instead of L over G. So here, T is still the period. It's the amount of time for one cycle or one oscillation of the spring. It is in seconds. And then M is the mass that's attached to the spring system, and it has to be in kilograms. And K is the spring constant or force constant, again, of newtons over meters. Now, if you wanted to use this formula to calculate mass, then the conversion for this would be T over 2 pi all squared multiplied by K. Okay. If you want to solve for K using this formula, you could do mass divided by T over 2 pi all squared. Make sure either you use parentheses on that 2 times pi, or that you use divided by 2 and divided by pi when you put that in the calculator. That's a common error when this gets put into the calculator. Also remember that the pi button on our calculators is next to the letter H, okay, on the TI Inspires. So there's important things to remember about the spring's period, just like there are important things to remember about a pendulum's period. One of those, the larger the mass is, the longer the period's going to be. There is a proportionality between that because it's going to stretch it further, so it's going to take it longer time to return to equilibrium and go through a complete oscillation. The stronger the spring is, so the larger the K constant, the shorter the period's going to be, and that's because there's an inverse proportionality with that. So the bigger the K, the shorter the time, because it's not going to stretch as far. It's kind of why your shocks on your car have a really strong spring constant or a really large spring constant, so your car doesn't oscillate or bounce up and down the road very much. And remember, period is always going to be in seconds. Always, 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 always. It is a time value, so it's always in seconds. Now doing an example problem of that. What is the mass of my car if the shocks have a spring constant or a force constant of 6,000 newtons per meter, and it oscillates with a period of 2 seconds when I hit a bump in the road? I like to hit speed bumps a little quick, unfortunately. My husband always tells me that's not good, which I know it's not good on my shocks. But this is kind of that thought process that after you go over a speed bump, your car does oscillate for a little bit before it comes back to a smooth ride. And so to find period of a spring system, it's T equals 2 pi over square root, or 2 pi times the square root of m over k. If we're looking for the m, we have to divide by 2 pi and square that to get rid of the square root. And then to get the m by itself, we have to multiply by k. So when we plug that in my calculator, I type 2 divided by 2 divided by pi. Then I hit enter. And then I square that number, and then I multiply by 6,000. That gives me an answer of 607.93 kilograms. All right. Hope this helps. And if you have questions, please make sure you contact me. Have a good one.